Hello everyone, my name is Nikita. I am from EC branch. My subject is chemistry and my topic is energy efficiency study of paper making drying process. Synopsis. The energy used in paper making, the need for multivariable process control, advanced process control, reduction in the energy used in paper making, some dryer steam reduction results from recent APC implementation projects. They are road making greater than 10% energy reduction to data plus consequent production benefits. Newsprint also greater than 10% of energy reduction to data. Towards further reduction of dryer steam use, results from current paper machine investigation of the potential for, for dryer steam reduction by better control of drainage by optimization of the dryer hood. Case study material from several paper machines. To ply board machines in England, Australia, newsprint machines in England and in North America. Conclusion. Energy used in paper making. Paper making is an energy intensive industrial activity. Here we have a block that paper type energy consumed. Energy was cheap and plentiful when present-day pulp and paper industry processes were designed. About 70 paper machines are still operated in the UK, but greater than 20 operated 50 years ago. Each machine cost ten of millions each. Not easy to change technology fact. The resting cost of energy has shut more than 10 UK paper mills in the last 3 years. The picture is reflected elsewhere in the northern hemisphere. Thus, there are strong incentives to reduce the energy in paper making. Dryer steam. The big energy user in paper making. The big energy user in paper making. It is known that the dryerization of a paper machine reduces sheet moisture content from 50% to 8%. M is equals to water by water plus fiber. Uses up to 80% of mill-wide energy but removes less than 1% of water from sheet. Consider 10 grams of thin stock laid out onto the wire at heat box. Advanced process control in paper making. Most processes in the pulp and paper industry are strongly multivariable. Control problem in the paper industry requires multivariable solutions. A paper making has many unused control variables because it has never been cleaned how to use them in a PID control law. Formation and drainages are jointly affected by the same input, often greater than 15 of them. Key quantity variables are often controlled using a PID loop that adjusts just one of several variables affecting the quality variable. Example: recycled plug brightness is controlled by bleach rate alone, expensive, ignoring other influences on brightness uplift. Advanced process control (APC) offers optimal multivariable model-based predictive control (MPC) subject to specified constraints. Profits can often be made by operating close to or at constraints. Why control a tank level to a set point as with PID when what is required is simply to keep the tank from overflowing or underflowing. APC was developed in oil and petrochemicals, still quite new to the paper industry. Energy reduction in paper making. Paper making using APC, some recent results. The following result arises from APC on paper machine making broad and paper machine making newsprint. Towards further reduction of energy use in paper making, better control of drainage, paper making, better control of drainage, better control of drainages, optimize vacuum power and steam saving, maximize solids content of sheet in entering dryer, reducing dryer steam use, provide better control of sheet moisture. Many influences on sheet drainages, amount of refining rate of use of chemical additives, especially drainage aids, stock consistencies, head box parameters, vacuums imposed pressure. All of these variables affect other sheet properties than moisture alone. Multivariable control can provide coordinated control of drainage and other quality and production variables. Thus, more intelligent control of drainage can have simultaneous energy reduction and quality improvement objectives, resulting in reduced steam usage in the dryer by draining to lower moisture contents, straighter sheet MD moisture profiles, hence straighter draw in the press section, better control of formation if measured online. Overview of drainages. Identify which wire section vacuum has an influence on drainage and what that influence is. Determine which other wet end and headbox variable also affect drainage. Apply process response test to the variables and develop a process model from these data. Recommend which of the non-automated vacuums should be automated. Suggest optimal settings for vacuums at the forming table and the former to maximize sheet drainage. Using either regulatory or advanced process control techniques, provide suggestions for the process control strategy for these vacuums and the wet end and headbox variables that are found to influence drainages. Reduce steam usage in the dryer by draining to lower moisture contents. Straighter sheet MD moisture profiles. Overview of recent drainage study of 2-ply broad machines. Propose. Determine the influence of a comprehensive set of wet end, headbox and Y section variables on drainage and sheet moisture. Sensors had been installed to measure sheet solids content online at 3 wet end locations: pre-former, post-former, pre-course. Study objectives. Identify which vacuum has an influence on drainage and what that influence is. Determine which other wet end and headbox variables also affect drainages. Recommend which of the non-automated vacuum should be automated. Using either regulatory or advanced process control techniques, provide suggestions for the process control strategy for these vacuum and the wet end and headbox variables that are found to influence drainages. Market competitiveness remains the strongest driver for energy efficiency solution. Historically, these industrial sector groups have been improved its energy intensity over a long period of time, which is primarily driven by overall market conditions, growth and competitiveness. Despite the disruption in the EU financial crisis, most sectors have recorded increasing growth trendy. Apart from petroleum refineries and non-metallic minerals sector group, the historical energy intensity trends for respective sectors. Industrial Energy Efficiency Database. ICF's IED is a database defining the technical and financial performance of energy efficiency technologies and opportunities, or Bundles of opportunities referred to as energy saving opportunities applicable within the processes of most industrial sectors. The database has over 230 ESOs with information compiled from ICF studies and other technical literature. The ESOs include both generic and sector-specific processes further to technological opportunities. ESOs also include management best practice MVPs refer to behavioral actions attributes to respective businesses management systems and incorporative best practices from various models such as ISO Energy Management Systems, the UK Carbon Trust Energy Management Matrix, Australia and New Zealand Energy Management Guides, USA Energy Star Management Tools, and Natural Resources Canada Office of EE's Energy Management Tools. The full list of ESOs under ED are listed. Process modeling. The set of processes, response tests, and selected running data has been used to build a preliminary process model. This model is preliminary in that it doesn't take into account change in process gain to grade and basis weight. Further tests would be required. As inputs, the model uses all the serviceable forming table vacues, headbox parameters, the bottom layer drainage rate transmitter, and the measured steam flow to the machines. It predicts a change in the online sheet dryness, wire section, power load, and MD moisture. The model was then used to determine which vacuums and other variables have the strongest influence on moisture quantity, quantify the effect of freeness changes. OK dryer built a simulation to evaluate various optimization strategies. Process optimization scenarios. A process simulator and model predictive controller have been constructed from the model. The simulator runs 10 times faster than real time. This allows different control and optimization scenarios to be tested and evaluated quickly. Scenarios first one. Electrical energy saving. Maintain the same pre-toxic dryness and steam consumption. Save 10% in total in electrical energy. Maintain at least 80 to 100 liters or minutes for more flow and control MD moisture to SP. Scenarios 2. Steam energy saving. Allow pre-coach dryer to move as required. Save 10% in steam energy. Maintain at least 80 to 100 minutes for more flow and control MD moisture to SP. Subsector share of energy consumption. Provide an estimated overview of a share of energy consumption between the subsector based on statistics analyzed from EUROSTAT. The Confederation of European Paper Industry, German Federal Statistics Office, National Statistics Institute of Spain, and Statistics Finland. It is estimated that manufacturing of pulp paper and paperboard consumes over 98% of the overall final energy consumption reported under Eurostat for the paper and print sector from EU28. This is mainly attributed to the upstream processes of producing pulp, paper and paperboard, which is much more energy intensive in comparison with the downstream process of printing and product consumed between 27 respectively. Towards further reduction of energy use in paper making, better control of dryer. We, we propose two approaches to better control of the dryer. Use all the variable to better control of dryer sheets. The traditional regulatory approach to controlling a paper machine dryer usually use a three-term PID loop driven by the difference between measured and target sheet moisture. Control action is cascaded to operate on steam pressure in 3 to 7 dryer section aiming to meet the moisture target. Machine pulp produced by mechanically grinding the wood log into smaller pieces with water. The heat generated by the grinder process softens the lignin, binding the fibers. As a result, the mechanical grinding process separates the fiber from the lignin to form pulp, which consists of whole fibers and fiber fragments of different sizes. A multivariable APC approach to dryer control could be based on building separate models of the effect on sheet moisture of the steam pressure in each dryer section, the differential pressure across each dryer section, the condensate recovery rate from each dryer section. Differential pressure and condensate recovery rates are seldom used in closed loop dryer control scheme. Neither operating practice nor the literature provided clear guidelines about how to use these variables to optimize dryer performance. Optimize the operation of the dryer hood. The traditional regulatory approach to control of the hood environment of a paper machine dryer also usually use three terms PLD loops. Actually, the hood is a multivariable system requiring real-time optimization to minimize energy use. In a current project, we have found modelable effects on sheet moisture, and in a current project, we have found modelable effects on sheet moisture and dryer steam use of variables such as inlet air flow rates on both the wet side and dry side, exhaust air temperature targets, exhaust air humidity targets. Conclusion: a significant reduction in the energy consumed in paper making is possible using advanced process controls methodology. Model the machine as a multivariable process. Use this model to design a multivariable model predictive controller. Run the controller with powerful real-time optimization functionality. Evidence to date show there are good prospects of reducing the energy used in paper making by at least 20%. 10% reduction from better control of wet and stability. Up to another 10% reduction by better control of sheet drainage. There are prospective further benefits not yet qualified arising from better control of the dryer using all variables, dryer variable optimization, and better regulation of the dryer hood. Thank you.